So just a quick warning, সেটা হচ্ছে please be a little careful when you are handling your Microsoft Teams app or the browser website. Why? Because last time we missed almost half of the class. So might be maybe it was a technical glitch, or maybe someone accidentally clicked on the stop recording button. Okay, so that's why please be careful, because when I'm presenting, when I'm in a presentation mode, I do not really have any access to Microsoft Teams. That means if I do not have any access, I do not know whether it is being recorded or not. So yeah, I would request you to please do not in any way click that stop recording button. Okay, so with that, let's begin today's class. So today we are going to talk about GIS. What is GIS? So if you can recall, in our last class, we talked about the three philosophies involved in GIS. And these three philosophies, we say that they are geography, and they are mathematics, that is the statistics. And the third one is the technology. And we also talked about that the quantitative revelation of geography happened in the 1950s. So we also discussed about Brian Barry's and the space cadets, their space cadets. I think I have already shared that article with you in previous semester, or even before that. If not, and still, I will share it again. Just go through it. It's really fun reading, and it's very informative. And once you go through this article, this memoir, you will it's not that very long. You will have a basic idea about geography, how the geography was evolving throughout the time, especially in the mid 50s or at the end of the 50s, when the data, that means the quantitative data, were coming into the geography, and the shape of geography, the practice of geography was having or experiencing some paradigm shift. And afterwards, when the technology really improved, when I'm talking about technology, what I mean is the computing technology. It's really improved. I mean, when the Brian Barry and others, the space cadets, when they were using different software, when they were calculating in different platforms, the geographic calculation, I mean, they were using machine language. They were learning machine language. They were doing programming in machine language. And then in 1958 or so, they started learning Fortran. So Fortran is a computer language. You already heard about it in 2207. So Fortran is still very powerful and still being used till today. Okay, why? Because it's very close to machine learning language, so it's very fast. So whenever you are making a software, or you are doing a program, or you want to solve a complex problem in a very short time, that is shorter than other programming languages, so people tend to use Fortran. So that's why it's still popular. So they started learning or using Fortran for solving the geographic problems, the quantitative problems in early 1960s and late 1950s. So what I'm saying is the introduction of such programming abilities, and then multiple development of multiple software as well as hardware, improved hardware, introduced or helped or influenced the introduction of today's GIS. So basically, that is why basically when we talk about GIS, and if we ask what this is, and if we subtract G from GIS, if you minus G, if you remove the G, then it becomes IS, that is information system. And that is very much true. Whenever you will be working with GIS, you will feel like that. Always you will feel like that you are working with some information system, because all you are doing is you are manipulating data. And then by manipulation, you are deriving some results. And by having that result or retrieving that result, at the same time, you will be storing the existing data as well, or you will be replacing existing data as well. So that is very similar to an information system. And that is why what we have right now is we have geography and then information system. And then when we have geography and information system, the link that we have is based on statistics or mathematics. Okay, so the numbers, the qualitative idea of geography is being connected to the information system based on the numbers. That is the philosophy of the mathematics, or the quantitative aspect of geography. However, time to time, there will be some qualitative aspects of geography being produced or used in GIS. For example, you have some qualitative information that you want to publish in GIS, or you want to incorporate in GIS. So what do? You create a map. So that map doesn't really contain any quantitative information, rather it contains qualitative information. So whenever I'm saying that GIS is actually the blend of three philosophies, I do not really mean that we are only dealing with quantitative geography. We are also dealing with qualitative geography, because I say the first component is the geography itself. So geography contains both qualitative and quantitative geography. And then the statistics comes in and influence the quantitative geography, and the technology comes in and form this information system based on the technology and the statistics. Anyway, so this information system is very, very unique. Why? Because this information system is applied on spatial data. That means this information system deals with locational information. So other information systems, they do not really incorporate these spatial problems. They do not deal with spatial problems. They do not deal with any locations. They do not include any X, Y, that is latitude and longitudinal data. Okay, so any other information, for example, accounting information system, AIS, if I'm not wrong. So that subject, or that genre, or that field of study do not really talk about any location. That one only talks about something that is relevant to accounting or such. So any other information system, even if you think about any database, they do not really separate any spatial and non-spatial data, because to them, spatial is not anything special. Okay, so everything is just data. So even the location, by any chance, if they do include the locational information, they do not treat it like location. They just treat it like any other information, that is aspatial data, non-spatial data. Okay, but whenever we come to GIS specifically says that I need spatial data to deal with a problem. So that means whenever you are making some input of latitude and longitude, GIS will always consider it as spatial data. That means it will take location as location. And the rest of the data, which are attributes, for example, you go to a point and say that, okay, this point is a tree, or this point is a house. So you are inputting two types of data, two types of information. Excuse me. So the first information that you are making input is the locational information. You are making, you are inputting X and Y. And then the second sort of kind of information they are making input is the attributable information, or attribute. So this attribute is the type of entity. So you are saying, when you are saying this is a tree, that is attribute. The tree doesn't really include any locational information. When you say that this is a tree, if you come to my class and you say, oh, sir, I have seen a mango tree. So, or if you say that I have a mango tree, I have some mangoes from that tree. So, and then when we look into those mangoes, and when you talk about that mango tree, we do not really know where that mango tree is. So all we know that you have a mango tree, and in our mind we could have an image of a typical mango tree. So now you come to our class, and then you open up GIS software and you input some X or Y coordinate, or you start Google Earth Pro or Google Earth software, and then you input some coordinates, and then you zoom into that coordinates and you say my mango tree is located there. So that is the difference between attribute and then spatial information. So spatial information always denotes the location, whereas spatial data, that is attribute data, they talks about non-geographic or non-spatial information. So then I have been talking about spatial and geographic, over and over, but there is some distinction between. There are some distinctions between these two terms. So geography is related to Earth's surface and near Earth's surface. So that is atmosphere. So when we talk about, I'm sorry, that is not really atmosphere. That is atmosphere, and also, in some depth to the Earth. So below the Earth's surface, it could include the below the Earth's surface. So when I say below the Earth's surface, what do I mean? So you have one, you have a hill, and then you have a mine there. That mine could be of any minerals. So when you are mining, that means you are digging through that hill, digging through the surface. You are going deep into the Earth, surface. So that is what I mean by this near surface term or the phrase. So geographic, when we talk about geographic, remember, it's always revolving about around Earth. But then when we are talking about spatial, that could include any space. And then that's including geography. So that is including Earth. So by any space, I mean it is any space. You could be at the center of Earth, and you could say that that is my spatial location, or that is my spatial information. You could be on Mars, running or walking or doing anything. So that is also part of spatial, that information that you send will not be geographic, etc., etc. Furthermore, if you think of the micro scale technologies, for example, you are dealing with some medical imaging that I have pointed out here. So let's say you are doing some ultrasonography, or you are doing some sort of other technologies to look into your body or somewhere else, some inside, some quantum scale things. So that would be considered as spatial information as well. Or so why do we always say spatial rather than geographic? Because it's more convenient. Whenever we have geographic, or whenever we say geography, we have to be very limited within Earth's surface. But then whenever we say spatial, we do not really have to be limited to Earth's surface. We can be anywhere. For example, just now I said that the quantum something, okay? So at the quantum scale, you are observing something that could be spatial. Or you are observing something at a very nano scale. For example, you want to test the safety of a car. So what do? If you have ever seen how they test the safety of a car, they put multiple dots on the surface of the car, and then they set up multiple cameras, and the car goes very fast, and then hit on a surface, onto something, and then they took these images and they actually calculate where are the most damaged area, which one is the vulnerable areas. So the things or the scenario or the phenomenon that I have just described is part of photogrammetry. So photogrammetry is also part of, or also uses spatial information. It's not necessarily geographic, although the test is happening in a geographic surface, that is on the Earth's surface, but it's not necessarily geographic. It's rather spatial, because the dots, they are located on the surface of a car or surface of a robot, or sometimes they could be located on surface of Earth. And then we are taking measurements of these points, very precise measurements. When I say precise, that means it's very detailed information. You are talking about like a very nanoscale, okay? So even nanometers changes you are observing. So you take these measurements, you make some automation, and that is on the surface of a car or any object, not on the surface of Earth, although that object is on the surface of Earth. So that is why that photogrammetry is also a big branch of GIS, or it's very close to GIS. If you do masters in GIS in a good university, they will teach you photogrammetry as a subject, because that is very much related to GIS. So you see, that is why in GIS, most of the time we talk about spatial data rather than calling it geographic data. So now, in last class, someone asked me about is remote sensing is part of GIS, either this class or in 3205. So here is the answer. So when we talk about spatial technologies, we have three broad technologies. One is GIS, one is remote sensing, and then another one is GPS. And they are interdependent. So how are they interdependent? So GIS deals with solving problems in geography, in any spatial problem. It's not only geography, but also any other spatial problem. On the other hand, remote sensing works in two ways. In one way, remote sensing collects data to be used in GIS. In another way, remote sensing itself is a science that involves multiple field of studies. For example, it involves engineering, it involves programming, it involves the subject where you want to apply remote sensing. For you, for example, you want to apply it in disaster management. So how can you apply remote sensing in disaster management? Let's assume that you do not want to solve any geographic problem or spatial problem. That means you do not want to do any analysis which involves GIS. You want to simply use remote sensing for your problems. So what do you do is you go to any remote sensing satellite or any data source, you pull that data and you observe the changes, or you want to find something. So one quick example could be, let's say a cyclone is approaching towards Bangladesh, and you want to find out, the category of cyclone and how does it look like. Also, what is its speed, the propagation speed. So you go to any meteosat or meteorological satellite. Okay. So then what do? Is you collect the scenes and then you observe and you find out your answers. So that does not really include anything of GIS. It's independent. You are only using remote sensing. And then, for example, you want to find out the extent of flood. Just like the example that we made in 3205, you want to find out the extent of flood. So what do? You go to any SAR image, that is synthetic aperture radar, which is still remote sensing. You get the data, you process the data, and then you find out, you identify the extent of any flooding. Now, you say that, okay, so I want to find out what are the damages based on these floods, or you want to find out why these floods are happening in some specific locations but not in other specific locations. So if you want to solve such problems, then you have to come to GIS. You have to now incorporate the remote sensing data or bring remote sensing data you have to bring that remote sensing data into GIS. Sorry, there is a noise going on. I closed my doors, but still the noise is coming in. Where was I? Okay, so right. So in remote sensing, there are other fields of studies are involved. For example, engineering, I mentioned. So you want to send a satellite, or you want to send a plane, okay? Or you want to send a drone, which will collect these remotely sensed data. So you see, the engineers, they have to build that satellite. Engineers, they have to build that drone with having the idea in their mind that this will be used for remote sensing purposes. That means maybe the camera that it will be holding, it will be quite heavy. You see, I talked about camera. So now comes the technology of camera. What sort of camera will you be using? Will you be collecting some optical images, or you will be collecting some SAR images, which is radar, that is electromagnetic information, or the waves will be sent out and then collected again, or you will be talking about laser technology. So different technologies are blending in, and also it's really important to note down where you took or released the signal and where you received the signal, because without having identified that location, you will not find out where these informations are actually. So for example, let's say you took a plane, you flew over Chittagong Hill Tracts, and you have collected the landform. Okay, so if I draw this one, let's say these are the hills, and then that's your plane. Sorry for this such bad drawing. That's your plane. So you came in from this way. Okay, so you sent your signal from here, it went down, and then it came up, for example. So this question also came up in previous classes. Some of you asked that since the planes or satellites will be moving very fast, how can we record them? or will we not be having some sort of anomalies or change in location when we will be receiving the the signal back? And my reply was, it's very fast. I mean, the signal travels in a speed of light, so it is very fast. So for the short distances between the surface of a hill and the plane flying overhead does not really have any significant differences, since the signal is or signal travels in speed of light. So you take multiple shots, and then in your computer you have developed this form. But now the problem is you did not, I mean, you have this image, you have these forms, but you did not, you know that this is the height, let's say 500 meters or 100 meters. The height of this is 100 meters. So you have put down it on a scale. So that's 100, 50, and 0. That is mean sea level. But now you are having some problem because you do not know which hill or hills were they, because you forgot to turn on your GPS. Since you forgot to turn on your GPS, you have these lines on your computer, but they do not have any locational information. So you do not know where they are located. And how can you go and find out their location? That is impossible. Okay. So because you are flying and you did not really took down on your plane, the pilot didn't took down where the machine went on and off, because the pilot was, handling the plane. He or she was busy handling the plane. So that is why GPS also very important. So GPS, every remote sensing equipment are equipped with a GPS, a very sophisticated GPS, which can track in real time where the things are. So, and then this GPS, it's also connected with the equipment that is responsible for sending out the signal or recording of the signal. So it specifically tells you that, okay, so this one is located in X and Y coordinates. This one is located in such XI and YI coordinate. This one is located, and so on. So that way, you know the coordinates of each specific shots or points or the line or the points on the line. And that way, now you can identify, okay, so this is the hill which is located in such location. So yeah, that's how it works. And also in GIS, whenever you will be collecting data, so remote sensing and GPS, these two parts, they influence GIS by handing out or giving GIS some geographic data, or helping GIS in some in data collection. So I already talked about the remote sensing collects data, process data, and then these data can be used in GIS for further processing or analysis. GPS sort of works in the same way. So what GPS does is you have your GPS, then you go out in the field, then using GPS, if that is handheld GPS, by using GPS, you can collect multiple lines, multiple points. You can come back and input that points or lines in GIS. For example, those who have attended our DMF first webinar on Youth Mappers, you have seen that software also has one option where you can incorporate the GPS points that you have collected with your GPS machine. So GIS also works in the similar way. And then if you have RTK survey machines, so kinemetric survey that is used for, so that those GPS devices are very expensive and very sophisticated. So what you can do with them is you can set up one GPS machine on your car, and then you can just drive around, go very fast. And you could also set up another reference machine in some distance. So these two GPS devices, the receivers, they will be connected to GPS satellites. And since these two GPS machines are located, and one is acting as reference, we will be coming back to this. However, let me just talk about them very briefly. So, for example, you have one GPS set up here, that is reference GPS device, and then you have your car. Sorry, it's very tough to draw on with mouse. So, and then I'm using my mouse pad, not even a mouse. So yeah, excuse me. So you have your car and you have your GPS device set up on top of this car. So your GPS device is connected with this GPS device, and this GPS device, which is very, very sophisticated, okay, so this one is connected with the satellites, multiple satellites. So these satellites are giving or identifying this GPS device or helping in identifying its location, the very precise location. So this one knows that, okay, my location is such X and Y coordinate. And this X and Y coordinate is very, very accurate X and Y coordinate, unlike handheld GPSs. So handheld GPSs, they could have accuracy of 15 to 20 meters. So 15 to 20 meters, they are very huge. Okay, so 20 meters is 20 times 3 is 60 feet. Quite long. So this one goes down to millimeter scale. Okay, so millimeter is very small. So if the error is millimeter, that means you can go off your actual location. You can go off for a few millimeters, let's say 5 millimeters. So 5 millimeters is very small. So you know your very precise location. So this GPS device is equally powerful to this device, with this device. And then it can also identify its location precisely. So this one is also connected with satellite. This is also connected with satellite. They both know their very, very precise location. Okay. And now you connect with each other. They themselves are connected with each other. And why? To improve the accuracy. How? Because let's say this one, it finds out that, okay, my coordinates are x1 and y1. And this one finds out that my coordinates are x2 and y2. So if they are x2, x1 and x2, y1 and y2, then you can find out the distance between them. Okay. So when you are finding out the distance between them, so now you have another parameters when you are finding out their location. So the one location is their x and y coordinates. So these x and y coordinates, as I say, they could have some error of few millimeters. Okay, but now, so let's say this is the point 1, and let me change the color. Maybe this would be better. So this is second point. Okay, so this is the actual location. Okay, and this one is what getting from satellites. This is what getting from satellites. So they are off few millimeters from their actual location. So now, what do? You are trying to find out their distance. Okay, so if this one, when you are measuring this distance, so it will giving you another scale or another, it's bringing in another parameter to when you are calculating. So because of this distance, I mean, from these satellite signals, you are getting that, okay, we are, let's say 30 meters apart. And then when you are measuring this distance, And when these devices are measuring the distance between them, it's telling them that you are not really 30 meters apart, you are 30.1 meters away from each other. So then this one, when it's, say this is the reference and this one goes, the car drives this way, so it will now driving 30.1 meters away. So the basic idea is very similar to this, the explanation that I made. I think you understood this one. So that's how data are being collected. So the car drives in this way, and when it comes back, for example, it drives in such way, and then it comes back, you collect this data, you bring this data into GIS, and what you have now, you have one road network. Okay, so by using such technology, you can have the road map or the street map of Dhaka within maybe a few weeks. All you have to do is you have to set up a machine, and then you have to drive around Dhaka city. That's all. So the information system. Let's go back to these definitions, the information, and then break it down. So what is a system? A system is a group of connected entities and activities which interact for a common purpose. So whenever you have a common, you want to solve a problem, that is what it says. You want to solve a problem, and then multiple objects or multiple entities or multiple activities are working for it, working towards it, to that solution. And doing so, they are interacting, they are collaborating, coordinating between them. So that one is a system. For example, your car, or if you ride a bike, that is bicycle, there are tires, there are handles, there are brakes, there are chains, there are pedals, and there is a seat. So all of them together are working to go forward. So their purpose is to go forward. So someone, the user, will be pushing the pedal down, and then the chain will move, and that will activate the tires for rotation. So the tires will rotate, and then you will go forward. And for in any reason, if you have to stop, then you have to press the what do you call them, brake handles, and that will pull the brake shoes, and the brake shoes, they will start squeezing the tires, the inner part of the tire, and that way that the tires, do we call them tires, or the wheels stop rotating. Okay, so you see the multiple objects are working together to solve or for a common purpose. So that is a system. And the information system includes or deals with information similar way of a bicycle. So the system of a bicycle works to go forward, and the information systems works with the information to derive in some sort of decision to find out the solution. Okay, and then to process data, store data, and then satisfy the customer, the clients. So if we look into how GIS is located into information system, then we have this chart, these classifications. So we have information system, and then we have non-spatial or aspatial, and then spatial systems. So in aspatial systems, information systems, we have management information systems, which is resultant into DSS. And then in spatial systems, we have geographic information systems, and then non-geographic information systems. In geographic information systems, this is just take note that this list is not exhaustive. That means it does not include all of the systems. It's just a broad classification. So land information systems and other GIS, they are part of geographic information system. So you may ask, why did I put land information system here? And for all other GIS, why did I put other GIS? Why didn't I mention of other GIS or other information systems? Because land information system is very important. Wherever you go, in which country you are, in which planet you are, even if you go to Mars, you will find that people are fighting for their land. Okay, they are always trying to occupy and declare that this is my property. So that is why land information system is quite important. It used globally or even beyond our globe. So yeah, and then there, if you look into our country, there are lots of conflicts over land as well. So in Western countries or in modern countries, what they did was they precisely using GPS, they precisely did their measurement, they precisely drawn their boundaries of every land parcel. Okay, every ownerships are associated with every land parcel. So in that way, there is no conflict, there is no problem. So GIS comes in very handy into this. And GIS manages a large, very large part of land information system. So these land information systems are based on two types. One is the parcel-based and another is non-parcel-based. And then the other GISs, they deals with natural resources and other problems. For example, you want to find out, how the urban areas are evolving, or how the parks in urban areas, in cities, more specifically in Dhaka cities, how are they playing their roles in quality of life? So that one falls into socioeconomic analysis as well as natural resources. It's a blend of these two last categories. But then if you are talking about, okay, how the river systems are changing through the time by using GIS, if you want to find that, that goes to natural resources. And now, let's say in another example, you want to find out the fire risk zones in Dhaka city based on different parameters. So now you are talking about socioeconomic problems, and you are excluding natural resources from your study. And when we come to these non-geographic information systems, we have basically we have designing platforms as well as cartographic platforms. So, for example, in computer-aided mapping, for example, CAM, or in design, what you can do is you can design a house. You can, which is not really GIS. You can design a map, you can create a map, which is a cartographic aspect of GIS, but if you create a map in CAM or CAD, it will not really have any coordinate information. Okay, I do not know whether you have used CAD or CAM previously, but if you do, then in CAD or CAM, you do not really include any coordinate information. Sometimes you do, yes. Sometimes you input a coordinate system, but then to find out the next point or to draw a line, what do? Is you find out the angle. So for example, you have a point here. So this point was input by an XY pair, okay, a coordinate pair. Now in GIS, if you have another point here, you draw this point and then connect the line, okay? So this point would need another pair of X and Y coordinates. But in these softwares, what you do is you find out the angle. So if this is 0 angle, I have to go 30 degrees. So you say, okay, so for imagination, let me draw this. So this is the reference line, which is 0. and then 30 degrees or such. Okay, for example. And now you say that, okay, since this is 30 degrees, so I'm going to go this way. And how long do I have to go? I have to go, let's say, 2 inches. So you go 2 inches and you stop here. So it does not, although initially it used a coordinate system, and then for the later parts, it does not really include any coordinate systems or consider any coordinate systems, because this one is mostly for designing purposes. So that is non-geographic information systems. So now, why GIS matters? Let me quickly check the time. We have time. So why GIS matters? So this, the idea behind it, we already talked about it in our very first class. We said that location is very important. Where the things are happening is very important. And anything on this earth involves to a location. I mean, everything, almost everything that is happening somewhere. That is what Longley says. Okay, so Paul Longley, one of the authors of our textbook, said that almost anything happens somewhere. Okay, and that is very true. Even if you think of the time, if you do not change from your physical aspect, or if you change your location, you do not really have any time. Just for example, everything on Earth, on this universe, were stand still. They do not move. They do not grow. So time is very relative form, and from that aspect, there is no time because nothing is changing. And how do we measure time? We measure time based on the changes. For example, right now I'm moving my hands, talking. So these words are coming out from my mouth, and then I say that, okay, I spoke for last 45 minutes. That's how I'm measuring my time. And then the time when it measures, I'm looking into the dials of the seconds and the hours and the minutes. And I'm saying that, okay, the time is changing and so on. So the location, even for the time, is also important. And whenever talk about anything, any aspect, everything has their locations. You have your locations. You are not located at the same place. I mean, at this very moment, if someone is located in Dhaka, someone is somewhere else. Even if you are in Dhaka, I'm in Dhaka, but you and I, we are not, standing or sitting side by side. We are farther away. We are some space away, etc. So every entity, almost every entity has locational information, and anything that is happening, that one is happening somewhere. And then when it comes for disaster management, it's even more important, because to disaster happen, and any disaster, it happens over some place, be it a cyclone, be it a tornado, be it an earthquake, be it a fire, anything, any sorts of disaster, even the pandemic. Okay, it's happening inside your body. The viruses, they are attacking your cells. Okay, so the cells are getting destroyed, or they're alternating, they're having some problems, your body is not working, but the problem is at global scale. And then when we say global scale, we are talking about space. That means the global, the entire world as space is happening. Okay, throughout the space, throughout the world, it's happening. So that is global. So I say throughout the world, the space. So to further explain, knowing where some things happen is very, very important. For example, the position of your country boundaries. Okay, where your boundary, where is your country? You might start walking in north today, and then somehow you can become in China, and then if you go further, you will become in China and India border. Okay, and you might be in at the middle of a battle or at the middle of a war. And then, for example, location of hospitals. So right now, hospitals are very important, and right now, knowing which hospitals have ICU facilities, or where they can treat you, or where they can test you for COVID-19 is also important. Okay, it's even more important. So knowing only the hospitals is not suffice. You have to know more details of that hospital, what they can do, what they can offer. Okay, so from that aspect as well, you have to know your location and the location of the hospital, and how long would it take to reach to the hospital, or to reach the hospital. And then also you have to find out which routes will you be taking to reach to the hospital. Can you go straight, or you have to go through a different street? You have to follow a different path or different way. Okay, can you? Is it in walking distance, or you have to drive there? If you are going to drive there, can you go there by rickshaw, or you have to call ambulance, or you have to call a taxi to reach there because it's a little further away? So all these informations, they are important, and all of them are associated with locations. So and so on. I'm not going to discuss all these things. I think you have understood already. If not, ask me questions after the class. I will try to answer those questions. So based on all these discussions, I think we understood that GIS is built upon knowledge from multiple study of fields, and the important ones are geography, cartography, computer science, information systems, mathematics, and so on. And so why GIS is special? So I think this one already I have talked about. However, a few things that I have left out, I will discuss them here. So multidimensional, I have already talked about this one. You can use it is multidisciplinary and multidimensional. You can use it in different purposes within a single field of study, or you can study this one by incorporating multiple disciplines. It's voluminous. So geographic information system, it requires data. So far, we are talking about geographic information systems. Remember this. So far, we are talking about geographic information systems. We haven't talked about geographic information science yet. So the system is voluminous. It deals with data, and it requires terabytes of data. It might require terabytes of data if the problem is such. Okay? And then it requires, since we are dealing with locational informations, these locational informations has to be on some plane. That is, our Earth is round. We say that it is round. And if it's round and we're on it, that means all the locations are on a round surface. But the computer doesn't really deal with this round surface. It can, but we do not. So what do we do is we project this round three-dimensional surface onto a flat surface. It's sort of very similar method of you have a tennis ball and then put some color on this tennis ball and then throw it on a wall. So on the wall, you will have an impression of one side of the tennis ball. The game that, I mean, all of the kids played when they were kids. Okay, all of you have played when you were kids, I think. I did play the same game. Whenever we were waiting for friends, we have a tennis ball, and then you keep throwing the tennis ball onto a surface on a wall, and then it's coming back, you are catching it again. But then with every hit to the wall, it's leaving some marks on it. The marks that is coming from its one side of its surface, okay, or part of that surface. So that's how this projection works. And then geographic information system has unique. Anyone said anything? Okay. So next point is the geographic information system has unique analysis methods. Why? Other information systems, when they are doing any analysis, they are not really thinking about any location. They are not really dealing with any latitude longitude problem. So this latitude longitude, the coordinates, it contains two information, latitude and longitude. So when we are saying that it's only one extra component of the information system, that is coordinates, but in reality they are actually two components. So that is also another uniqueness that we have. And then whenever we are tracking any changes, whenever you are tracking changes of GDP or economy, or you know, the per capita income, etc., etc., you are just observing one single parameter, and then based on that parameter you are saying that, okay, my result is such. But then when you are talking about the changes of floods, the extent of floods, you are dealing with where the floods are the flood is happening. If there is water, yes or no, you are saying yes, there is water. And then the next thing you are saying, that's at which point. Okay, so when you are dealing with a single phenomenon, that single phenomenon is having three components, at least three components. One, why this phenomena is happening, that is water. Is it inundated? Yes, there is one component, the inundation. Another component is latitude. Another component is longitude. So you are observing the changes of three things. So from point one, if you go to point B, the automatically is latitude and longitude has changed. And then in point B, you again observe, is it inundated or not? You say this is not inundated. So you say this is not flood, but point A was flooded. So you understand why the analysis methods are quite unique and different than other information systems. And analysis requires data integration. This one has already been discussed. Data updates are expensive and time consuming. We will come to that, but briefly, if you want to, let's say, for example, you want to update the road network of Dhaka, how long would it take? And by update, I mean that you have to work very precisely. You have to have very detailed information. And detailed information means your geographic coordinates has to be very, very accurate. So for updating the road network of Dhaka, you have to go with GPS devices into multiple roads, and then you have to wait there to make it stabilize, and then move forward, take measurements, move forward, take measurements, move forward, take measurements. So it will take very long time, or it might take very huge manpower. So you might appoint, let's say, I don't know, maybe few thousand people, and give them few thousand GPS devices, very expensive GPS devices, and they will go out and they will complete the collection of data within 1 week. So you have minimized your time, but your expense became skyrocketing, became very, very high. Okay. So map displays require fast data retrieval. I think I have shown you the Google Earth Engine in previous classes. So you see in that Google Earth Engine, in the example that I shown you, in that example, based on the internet connection, the maps were loading quite slow or quite faster. So the same thing happens. How fast can you display a map depends on your data retrieval. How fast can you collect your data? So this data collection could be from the reality. You might go this, for example, the road network of Bangladesh. If you can collect it within 1 week, you can display your map after 1 week. If it takes 30 days, you can display your map in 30 days. And then when you put all this data, because your data will be very huge, because this is raw data, this is not processed. When you put this data, and then when you display, you want to display on a computer, if you use a very fast, the very powerful machine with lots of processing power, then that computer could display it very fast. Whereas a slow machine, because that machine's data retrieval power is very slow, so it will display that map very slowly. And now, when we talk about the knowledge bases, so this one I think I have already discussed when we were talking about philosophical aspects of GIS. So part of it already discussed when we were talking about that. So this one actually deals with or talks about which part of which field of study are being used in GIS. So from computer science or information systems, we are dealing with graphics, visualization, database, system administration, security, and so on. And then from geography, we are dealing with cartography, geodesy, photogrammetry, landforms, spatial statistics, and so on. And then when we want to apply them, they are very highly applied in public administration or public admin, then planning, geology, mineral exploration, forestry, and land management. Land management is not listed here, but land management as well. So after this discussion of three classes, now if you ask what is the definition of GIS, we do not really have any specific definition of GIS. There are many different views of GIS. Since the subject itself is very, very broad and it's multidisciplinary and it is used interdisciplinary, that means one discipline can use it. I mean, inside the discipline, it can use these techniques can be used, this tool can be used, and then it could be used in intradisciplinary as well. So two disciplinaries can use it together to solve a single problem which requires both disciplines. For example, flood management, it could be incorporated by or used by civil engineers and then hydrology experts. Okay, so water resources engineering. Two types of engineers could come up and then decide that, okay, this is the place where the dam should be built. So you see, it's intradiscipline. So, however, when we try to generalize these, the idea of GIS, we think of the requirements for a software developer, what that developer needs, and an emergency manager, that is you, a tourist, town council, and multinational corporations. And by this, what I mean is the products of GIS, when we will be produce them, we have to think of the end user. So if you do not know what end user is the user who is going to be using the product at last. So that means consumers. So for example, as an emergency manager, your concern would be where the disaster is happening. As a tourist, your concern would be where are the attractions. And then if you have seen a tourist map, you will see that in tourist map, they do not really maintain any scale. They do not maintain the scale of the distances. They do not maintain the scale of the sizes. Okay, the sizes are not relative. So sometimes if the attraction is very popular, sometimes you will see them in big icons on your map. For example, our National Museum could be an attraction. So the National Museum, the photo of it, the icon of the National Museum is very big on the map. And then, I don't know, the National Library could be an attraction for tourists. So that icon would be very large in that map. Whereas you will see the universities are not identified in that map because tourists, they are not really interested going to any universities and so on. So from these different views, you will see that what we have talked about. We have talked about applications. We have talked about size, data models, information systems, hardware, software, functionality, toolbox, data, cost, all those things. So when you want to define GIS, you can define GIS from any aspect of these and many more. So it depends on your what things that you do for GIS, and then what things do you do for GIS. So what are the things that you are getting from it, and what are the things that you are making to it. So I'm going to skip this one because I think I have already discussed this one. Later, rather talk about this one. So few of the authors define GIS, and we're going to read or go through their definitions. And whenever we talk about their definitions, you will see that these definitions, they always talk about data. That means they talk about the entire GIS is, in some way, they give a feeling that this entire GIS is all about data. You are manipulating data, you are capturing data, you are modeling data, storing data. So what do you do in solving a problem? Let's go through that picture. To solve a problem, the first thing you do is you have a problem, okay? So to solve that problem, you need a specific set of data. So you go and you collect this data. So that means you are capturing this data, okay? So you brought your data in. Now what do? You have to analyze this data, right? So for analysis, you do a modeling. So modeling is a very sophisticated way of analyzing. So you did a modeling. So that is you analyzing this data. And whenever you have collected the data, and then when you're analyzing this data, the results and the source data, they must be stored somewhere on your computer, on a database or an external hard drive. So obviously storage comes in. And then you have finally, from the model, you have your results. So the retrievals coming in. So that means new types of data are being retrieved from this model. And these retrieved data are again being stored to the storage. And now you have the result, but now you have to share the result, right? You cannot just keep it to yourself. That is no use. If you just keep the data to yourself, if you just keep the result to yourself, then it is of no use. No one is knowing about that. So that is why you have to share the results as well as you have to share the data. So right now, the sharing platforms are online mostly. Okay, all of the data, most of the data are being shared online through different websites. And then once the sharing is, you can share the data. Meanwhile, you can do further manipulation of the modeling or the data. You can do further analysis, and also your results, as along with the sharing, you can present your results in map or in graphical representations or even tabular form. So when I say presentation, there are three aspects. One aspect is graphical. Okay, so by graphical is by chart, bar chart, all these things, all the results. And then when I say map, I mean is you literally create a map. So you have collected data, locational information. And then what you do is you simply find out the map, the extent of the flooding. You print it, and then you present it, you share it. And the last form is the tabular data. So tabular data is, instead of publishing information or presenting information in graphical form by chart, bar chart, sometimes precise information are needed. So to present the information precisely, we put them in tables, or we list them in tables. So that is the tabular information. So based on these ideas, Warboys and Duckham in 2004, they say that a geographic information system is a computer-based information system that enables capture, modeling, storage, retrieval, sharing, manipulation, analysis, and presentation of geographically referenced data. And then National Research Council of Canada, they gave another example. Okay, so now they are saying that's okay, all of these things are right, but then what we are doing is especially referenced information or data have a unique characteristic association with a specific place on Earth's surface. So in previous example, it did not really included, although it said geographically referenced data, but it did not say where these data are coming from. Although whenever, based on our discussion on spatial and geographic, we know that geographically referenced data is located on the surface of or near surface of Earth. However, in the National Research Council's definition, it became more specific. So let's forget about all these definitions for now, okay? And then if you are scared of memorizing all these definitions, do not be scared. If you have, or if you can express your basic understanding of GIS, that is enough for me. Okay, so as long as you understood that you are talking about geographically referenced data, okay, not other data, but the geographic data, and then it's geographically referenced data. Okay, so it has some references. It's not just geographic data, it has some references. So geographic references data, and these data are being captured, stored, manipulated, modeled, retrieved, shared, and so on. Okay, so think of a problem, a geographic problem, and think of how you are going to solve that problem and which steps that you are going to take. If you can think of, if you can understand that, then defining GIS is very easy. So I think today's, this would be the last slide, this GIS, 2 more slides. So from the practical aspect of defining GIS, we actually think of its core components. So what are the core components of GIS? So the first core components of GIS is the technology that we have. And this technology are divided into 2 parts. One is the software, another one is the hardware. Okay. So in previous examples or previous definitions, even in your textbook, you will see that there are 5 basic components, or 5 parts of GIS. So the 5 parts are, you know, the technology, hardware, software, people, data, and procedures. Okay, so procedure is not listed here, sorry. Let me quickly add this one. Okay, so in previous definitions, we had hardware, software, people, data, and procedures. So these are the components. Okay, so we have hardware and software, we have data, we have procedures, and then we have users or people, those who are using all these things. But in present day, we have one additional component, that is network, which is internet. So everything is going onto the clouds in these days. Since everything is on the clouds, network is very important. In Google Earth Engine, we have said the remote sensing became based on network system. Without internet connection, it will not work. So even in GIS, in ArcGIS, not the ArcGIS that you will be using, but the software that Esri is currently focusing on, that software will not work without any internet connection, because all the data, all the resources are actually online. You access it from server, and then all you do on your machine is you run the accessed services. You utilize the accessed services. Okay, and all these services are coming from a server. So anyway, so if I ask you what are the practical definitions of GIS, this would be your practical definition of GIS, because in practice you need these 6 components. So the first component you need is the technical components, that is hardware and software. You have to have hardware and software. You have to have software installed on the hardware that you have access to. And the second thing you need is the data to work with. So in reality, we'll be collecting data and then bringing that data in your machine, and then process those data using the software. So when I say process those data with your software, here comes the procedure. What sort of processes will you be making? Will you be doing simple buffering, or will you be doing complex, you know, AHB, analytical hierarchical process? So will you be doing that? And who will be doing that? That's, I am saying, will you be doing that? So that's you. So you are the people, the users of the entire thing. And then sometimes all these things are connected. I mean, at present, all these things are connected with or by the network. So there you go, the 6 components of GIS, or the practical definitions of GIS. And all these things are involved. All these 6 components are connected to solve a specific problem. Anyway, so the final slide. So that's why ESRI, based on all these things, they defined GIS back in 1990. They said that an organized collection of computer hardware, software, geographic data, and personnel designed to efficiently capture, store, update, manipulate, analyze, and display all forms of geographically referenced data. So you see, now it has the aspect of this. Also, although this one is published in 2004, however, this one has all the components of these, have the components of this as well, and the components of practical definitions. And then you bring everything together. If you know the practical definitions, you bring in all these components of practical definitions, and then you associate them, you connect them with the process of geographically referenced data, and then voila, you have the formal definition of GIS. Thank you. Anyone have any question?
Sir, I do have.
Okay.
Sir, why do we actually in Bangladesh have less GIS or remote sensing specialists, whereas our neighboring countries has much more GIS and remote sensing specialists? Like India particularly they have their own agency, they have their own satellites, they have their own stuff. And on the other hand, Nepal has their own GIS and satellites expert, whereas they have only 3 to 4 universities, only one public university and other are private. Whereas Bangladesh has 37 public universities and private numbers are actually uncountable. So in terms of, and Pakistan also has much more GIS and remote sensing expert rather than Bangladesh. So why are we lagging behind in terms of expertise in GIS and remote sensing?
Okay, thank you. এই ব্যাপারে কারো কোনো কিছু বলার আছে? আচ্ছা, তার আগে আমি একটু করে বলে নিই, সাদমানের এই প্রশ্ন বাদে does anyone else have any question?
স্যার,
Yes.
স্যার আমরা যে দেখেছি যে দুইটা কোঅর্ডিনেট যোগ করে অ্যাঙ্গেল বলা হয় জিআইএস এর ক্ষেত্রে, অ্যাঙ্গেলটা মানে অ্যাঙ্গেলটা দরকার হয়, কিন্তু স্যার আমরা যখন কোনো লোকেশন বলি তখন তো আর অ্যাঙ্গেল বলি না, যে এটা এখান থেকে এত, দুইটা কোঅর্ডিনেট যোগ করার ক্ষেত্রে অ্যাঙ্গেলটা কেন লাগে?
আমি তোমার প্রশ্ন বুঝতে পেরেছি। সো ব্যাপারটা মনে হয় ভালো করে ক্লিয়ার হয়নি, আমি এক্সপ্লেন করছি। জাস্ট এ মোমেন্ট, এটা একটু করে ওপেন হোক হোয়াইট বোর্ড, তখন আমি তোমাকে দেখাতে পারবো। তো ওখানে আমি আসলে অ্যাঙ্গেল বলি নাই, ইন রিয়ালিটি আমি বলেছি তুমি যদি এই যে কম্পিউটার এইডেড ম্যাপিং ইউজ করো, হ্যাঁ, ওই সফটওয়্যারগুলো যখন ইউজ করবা তখন তোমার এরকম একটা পয়েন্ট থাকে, আর পয়েন্টের পরে তারপরে এখন তুমি যদি নেক্সট পয়েন্টে যেতে চাও, ওরা করে কি, ওরা একটা এরকম বলে দেয় যে এটা যদি নর্থ হচ্ছে 0 ডিগ্রি, সো 30 ডিগ্রি যাওয়ার পরে ক্লকওয়াইজ 30 ডিগ্রি যাওয়ার পরে আমাকে এভাবে যেতে হবে। এন্ড দেন কতদূর যেতে হবে, ধরো 2 ইঞ্চি যাব, 2 ইঞ্চি কি স্টপ। এখন এখান থেকে আমি আবার 180 ডিগ্রি যাব, সো এটার আসপেক্টে এখন 180 ডিগ্রি যেতে পারো, বা এটার আসপেক্টে তুমি 370 ডিগ্রি যাচ্ছ, সো তখন 370 ডিগ্রি তুমি কাউন্ট করেছো, তারপরে বললা যে আমি এখন ধরো 3 ইঞ্চি যাব, তো তুমি 3 ইঞ্চি গেলা। হ্যাঁ, সো এইসব সফটওয়্যারের ক্ষেত্রে অ্যাঙ্গেল হচ্ছে ইম্পর্টেন্ট, যে কত অ্যাঙ্গেলে তোমার রোটেশন হচ্ছে, কত অ্যাঙ্গেলে তুমি এক পয়েন্ট থেকে আরেক পয়েন্টের দিকে যাচ্ছ এবং কত দূরে যাচ্ছ। হোয়ারএস জিআইএস করে কি, এই যে 3টা পয়েন্ট, সে করবে কি, একটা পয়েন্ট, দুটো পয়েন্ট, এই তিনটা পয়েন্টের লোকেশন নিবে, এক্স ওয়াই কোঅর্ডিনেট গুলো নিবে, নেওয়ার পরে অটোমেটিকলি দে উইল বি কানেক্টেড। সো এখানে অ্যাঙ্গেল ডাজন্ট ম্যাটার। ওকে, কত কোণে তোমার এগুলো হচ্ছে, কত কোণে তুমি বাঁক নিচ্ছ, কত দূরে যাচ্ছ, ডাজন্ট ম্যাটার। অল ইউ নিড ইজ দ্য লোকেশন অফ দিস পয়েন্টস। সো এই পয়েন্টগুলো লোকেশন, অ্যাবসলিউট লোকেশন, অর্থাৎ তাদের অ্যাবসলিউট বলতে রেফারেন্স লোকেশন, কোঅর্ডিনেট, এই কোঅর্ডিনেট গুলো পেলেই তুমি অটোমেটিকলি তাদেরকে কানেক্ট করতে পারছো। এটা কি ক্লিয়ার হলো? হ্যালো, right. So any more question before we delve into Sadman's question, which is very important? I think এই সাবজেক্টের জন্য আরো বেশি ইম্পর্টেন্ট। ওকে, তো আর কারো কোনো প্রশ্ন নেই? তো ইন দ্যাট কেস তাহলে what do you think? সাদমান যে প্রশ্নটা করলো, এই প্রশ্নটা কিন্তু কোয়াইট ইম্পর্টেন্ট। ইনফ্যাক্ট তোমরা যেহেতু ডিজাস্টার ম্যানেজমেন্ট শিখছো, তো তোমাদের আসপেক্ট থেকে অনেক ইম্পর্টেন্ট। কেন আমি বলি, তোমরা কি কেউ সিলডাপে ট্রেনিং করেছো জিআইএস এর? যদি করে থাকো একটু হ্যান্ড রেজ করো তো। আর তোমরা যদি কেউ জিআইএস এর ট্রেনিং করে থাকো একটু হ্যান্ড রেজ করো প্লিজ। কেউ করো নাই? অলরাইট। সো সিলডাপ হচ্ছে বড় একটা, রাদার আমাদের ক্লাস যেহেতু শেষ হয়ে গিয়েছে, এটা যেহেতু ক্লাসের বাইরে, লেট মি স্টপ দ্য রেকর্ডিং, কারণ এটা তখন আরো বেশি লম্বা হয়ে যাবে।